7.3 Sum and Difference Identities. If you were in my pre-AP class, this is the last of the Chapter 7 sections that we saw before spring break. If you're a dual enrollment student, we also saw 7.4. It wasn't all of 7.4, but it was like the first half. But pre-APs only saw up to 7.3, and we pretty much finished 7.3 in all of my pre-cal classes. So let's see. Cosine and sum identities, or cosine sum and difference identities. There are two of them. One of them we proved, and it was a very, very lengthy process. I saved the proof over here to the side. I believe this is first period's notes. And for first period, we had this proof. Fifth period, sixth period, eighth period, that might have flowed a little bit differently, and it evolved throughout the day how I got this stuff done. But the proof will not be detailed here in this video. I'll probably go ahead and give another video or have a separate video where I prove all of these identities. So these identities will not be proven in this particular lesson. In this video, it's just we're concentrating on the application of the formulas and how to do practice problems, especially for my dual students, since you will have a test review for 7.1 all the way through 7.4. And I might upload even more videos in addition to these to cover more practice problems, maybe even out of the review. But most likely I'd want to do like a tutoring session online, maybe via Zoom or something else for the tutoring session, if there's enough of you that want that. So the sum and difference identities, there are two of them. The first one is the sum identity. That's not the one that we proved. It's the difference identity, the second on this list that was proven over to the side. So I'll give that one first. The one that was proven, cosine A minus cosine B. If we're using A and B for the angles, then it's going to be cosine A, cosine B. This one's plus sine A, sine B. And there's a bit of a mnemonic that I gave you guys in class to memorize these things. Cosine, 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 sine, sine, sine. Now the first cosine is here, second cosine's here, third cosine's here. First sine is the plus sign, second sine, third sine. So the first of the three signs, sine, 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 the first sign is a sign change. If inside the formula for cosine it's A minus B, then you change the sign outside to a plus. Same goes for the difference or the sum identity. So cosine, 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 whoop, I wrote A twice, that's a B. And then sine, sine, sine. So those are our two identities for cosine. There's two for sine, there's two for tangent, which we'll get to those in a second. First, example 1. So again, like I said, we're not going to prove those identities. The proof will be in a different video. Number 1, there are three parts to number 1, A, B, and C. And each of these are applications of the sum or the difference identity. And it depends how we choose to see it. For number 1, part A, cosine of negative 75 degrees, there's a bit of a simplification that you can apply. Section 7.1, the first section of the chapter, we notice that cosine is even. Cosine and secant are the only even functions. Everything else is odd, sine, cosecant, tangent, cotangent. Cosine's even, and what that means is if you negate the angle inside before you evaluate it, it's the same as if you had never negated the angle. So it's the same as if we were just calculating cosine of 75 degrees. So cosine of negative 75 degrees is the same as cosine of 75 degrees. So that makes it a little bit easier. Cosine of positive 75 degrees, the first thing we'd want to do is see if we can figure out how can we form a 75-degree angle by addition. So we're adding two angles, and we want to add them up to 75. So the idea is, if I knew what cosine of 75 was right off the bat, if that was one of my unit circle values, then I would just be able to recite what that value was. In this case, we didn't have 75 degrees on our unit circle. Those were restricted to 0, 30, 45, 60, and 90 degrees. And then anything else that was a reference angle equivalent to that, 75 not being one of them. 75 would probably reference back to 15 degrees. And 15 degrees wasn't one of those angles either. So I don't know how to get this one done unless you add or subtract two of the other ones we already did before. So 75 is an easy one. 30 plus 45 makes 75. So I'm going to go ahead and do it that way. This is the same thing as cosine of 30 degrees. plus 45 degrees, and you might want to put parentheses around the 30 and plus 40. So it's cosine of just 30 plus 45 together as a single angle. But we're trying to split this up using the sum and difference formulas. Since there's a plus sign in between, 30 degrees plus 45 degrees, you're using the sum formula. Now, memorizing both of these is not really important. You just memorize the mnemonic and it makes it easy from there. If it's a cosine, you start off with cosine, 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 cosine. So we already have the first cosine, second cosine, third cosine. And then sine, sine, sine. The first sign is a sign change. It was plus, now to minus. Sine, sine, sine. Which makes that easy, hopefully. So now we got to evaluate cosine 30, cosine 45, sine 30, and sine of 45 individually. Once we've done that, we can simplify whatever's left over, and we're done. Problem is we might not remember what those values are unless we had a unit circle handy, which I still have blank unit circle, or I still have a blank unit circle up in PDF format on the Google Classroom. So if you wanted to fill that up again, you can go ahead and do that. Print that out, as many copies as you want, whatever, and have that ready. You might already have one in your notes ready to go. You might want to pull that out for any homework problems that'll follow from here. So what I'm going to do, since I don't have one handy, I'll draw one, or maybe just a piece of one. Let's say just the first quadrant, and I'm going to try to draw and that was bad. I'll do another one. Actually, it wasn't too bad. I could have kept it. That's not much better, but like I said, we could just keep it. So this is 90 degrees up over here. 0 degrees down over here. Let's say, oh, x-axis, y-axis, 45 degrees right down the middle. 30 degrees is a little closer to 45 than it is to 0. So this right here is 30 degrees. And then 60 degrees is a little closer to 45 than it is to 90. So from here to here, that's 60 degrees. So it's a little ugly, but whatever. It works. So we have the intersections of those lines onto the unit circle, which is only the first quarter of the circle. And we also have these points down here too, the 0 degrees and the 90. At 0 degrees, if this is a unit circle, the radius is 1. That means the distance out from the origin is 1. This is 1, 0 then. Y-coordinate is 0 because it's on the x-axis. The x-coordinate is 1 because it is, the circle has a radius of 1. That's just a radius basically. 90 degrees. So for 90 degrees, we have the reverse, 0, 1. And then the points in between are easy to memorize. The one that's the easiest, in my opinion, to memorize is the 45 degrees. That is square root of 2 over 2, comma square root of 2 over 2. The other one that you're responsible for memorizing is this one. This is square root of 3 over 2, 1/2. Now, the reason why I say that those are the two that you're responsible for memorizing is because the 60-degree one is related to the 30-degree one. What you do is you flip the x and the y coordinates, you get 1/2 square root of 3 over 2, and that's because of the cofunction identities of cosine and sine. Cosine and sine are the same for a complementary angle. So cosine of an angle is equal to the sine of the complement of that angle and vice versa, which we'll see those again in this section. So you just flip the x and the y coordinate if we're talking about the complement of 30 degrees, which is 60. So 30 and 60 are complementary. So then the points have a flipped x and y coordinate. So that's my unit circle, which I'm going to use that over here. I might be able to show both at the same time. Okay, so we're simplifying this expression with the cosine of 30, cosine of 45. So cosine 30, looking at the unit circle, it's super easy. Cosine of 30 degrees is the x-coordinate at 30 degrees, which is square root of 3 over 2. Cosine of 45 degrees is this x-coordinate, but for the angle 45, so that's square root of 2 over 2. Again, super easy, hopefully. Minus, because there's a minus sign in that formula. Sine of 30, 1/2, hopefully you can see that. Sine of 45, square root of 2 over 2. Because we're only looking at the 30-degree mark and the 45-degree mark. And I have this expression, which is almost done. The only thing is simplification. So I have two products of fractions being subtracted. So I need to multiply each pair of fractions, and then I got to combine both of those results into one single fraction, I think. So I'm supposed to get one fraction in the end. Let's see how that works. The one on the left, square root of 3 over 2 times square root of 2 over 2, those are two fractions which need to get combined. And to combine two fractions by multiplication, you multiply across. Corresponding pieces get multiplied. So the numerators, square root of 3, square root of 2. When you multiply two square roots, as long as they have the same root base, which in these cases are both square roots, you're good to just write one square root and take the product of the arguments. In this case would be 6. So 3 times 2 is 6, so that's square root of 6. 2 times 2 on the bottom is a 4, minus 1 times square root of 2, well that's just square root of 2, and then divided by 2 times 2 again is 4. So that was the first thing that we had to do. The first thing that we had to do is take those products of those two fractions. Now I have two fractions left over instead of 4. Those two fractions are being subtracted, and I need to subtract them. So it's nice because they have the same denominators. So when we do subtract them, they'll be over 4 before I reduce, if we can reduce. I'm probably not going to be able to reduce because the one on the top, square root of 6 minus square root of 2, those don't combine. In order to combine square roots, they need to be multiples of the same square root. So as an example, if I had 3 square root of 5 minus 2 square root of 5, this would just equal to 1 square root of 5. You would subtract the coefficients. But you can't do the same thing like what we have here, square root of 6 minus square root of 2. Those don't combine because they don't have the same square root base. So it just stays as square root of 6 minus square root of 2. And that's it for this problem, part A. That is one way that we can write the expression for cosine of 75. By the end of the next section, when we go over double angle, half angle identities, there's going to be another way that we can express the cosine of 75 degrees. And that's going to have a square root within a square root. So there's different ways that you can do this. This is the answer we'd expect using a sum or a difference formula. So we'll try this again with letter B, which letter B, if you already look at it, it immediately looks harder. And it's not harder, it's in a different form. That's in radians instead of degrees. A lot of us are more comfortable with degrees versus radians. Radians are the preferred unit for mathematicians. A lot of the times it's a lot simpler, and math students don't catch on to that right away, why it's simpler. But either way, cosine 17 pi over 12. The problem with the pre-calculus class is you have to learn to deal with both situations. So 17 pi over 12. I'd like to see if I could split that up just like I did the 75 degrees in the previous part. So that way both of those two split up versions are angles that are found on the unit circle, just like we have here. So that's a little tougher because we have a fraction, 17 and 12. And then the pi is kind of intimidating. So there's two approaches. One, we own up to it and we continue. We just work in radians the whole way through and see if we can just conquer the fractional stuff. Or the other method is we can go the changing to degrees and then change back to radians. So change 17 pi over 12, convert it to degrees. Degrees we understand a little bit better, and then try to split that up into two angles. So I'm going to do both ways. So let's see. Or maybe a combination of the two. So we'll start off by changing 17 pi over 12 to degrees. So that's currently in radians. How do I change this to degrees? And I'm trying to squeeze that in over here because I don't have that much space. If I try to move over here, there's the proof that I was talking about earlier. 17 pi over 12. You want to change that to degrees. Now there's a formal way. The conversion factor for changing an angle measurement from radians to degrees is 180 degrees divided by pi. So the problem, or the thing that ends up happening is that the pi's cancel out and you're only left with a 180 where the pi was at. The shortcut that I've shown you guys in class, pi is exactly 180 degrees. So just replace pi with 180. So then I got to multiply 17, 180, and then divide that by 12. Now, I don't have to multiply the 17 and 180 in that order. I can divide the 12 into the 180 first, and then multiply the result by 17, which might be easier. 180 divided by 12 is 15, I believe. Now, the reason being, it's because 180 divided by 6, we already know is 30. Pi over 6 is 30 degrees. So 12 is twice as big as 6, so that means I got to divide it again. So 30 divided by 2 is 15. That's where I'm getting the 15 from. Now I got to deal with the 17 times 15. But a nice way to do this, you can split up the 17 15 is a nice number to work with, so I'm going to leave the 15 outside. 17, I'm going to think of as 10 and 7. I'm going to distribute those, which is an algebraic step, but you can use algebra to multiply big numbers. It makes the bigger numbers into smaller numbers, and it's a simpler problem. So that's 150. Plus, now I got to figure out 15 times 7. So 15 times 7, I know 15 times 6 is 90, plus another 15 makes 7. 90 plus 15 is 105. These are in degrees. So 150 plus 105 is 255. So that took a while. 17 pi over 12 is equal to 255. That's because I'm trying to do all this by hand. But either way, that's what this is in degrees, which I might want to not write that down just yet. The idea is we want to split this guy up, and then what that turns into, change that back to radians and pretend as if I had done that in radians the whole time. So 255, I know a couple of nice angles that add up to that. Let's say 210 is an easy one. I like 210 because it's on the circle. 30 degrees this way. So 210 is this entire angle this way. 210 is 30 degrees past 180. So 180 plus 30 is 210. That's why I'm choosing that one. Plus, what makes 255 from 210? 45? And 45 we already understand very, very well. So 210 plus 45 degrees. And that's how I'm going to do this. Now 210, if you remember this on the unit circle, 7 pi over 6. And this one, of course, we got to remember is pi over 4. So that's what I'm going to write in here. Cosine of 17 pi over 12 is the same thing as cosine of two angles added together. 7 pi over 6 plus pi over 4. That's what we have so far. So all that work just to figure out how to split those two up. So that's one strategy, is to change the current one to degrees, split up the one that's in degrees, and then each of the two that we got from the split, you change it back to radians. And then what we do is this. I'm going to pretend as if I knew that the whole time, and I know how to work with radians. So from this point on, I know how to do that. So 17 pi over 12 is 7 pi over 6 plus pi over 4. Now, if you're not sure, if you're not confident in what you currently have, which maybe I'm not feeling confident in what I currently have, 7 pi over 6 plus pi over 4 should add up to 17 pi over 12 in the end. And they do if you change the 6 and the 4 on the bottom to match to the 12. So I think they're both factors of 12. So we can write a 12 underneath and another 12 underneath. And the 7 over 6 changes to a 14 over 12 because you multiply both numerator and denominator by 2 to turn the 6 into a 12. To turn the 4 into a 12, though, you need a 3. So 3 on top. 14 plus 3, 17. It's exactly what we were supposed to get. So what I'm going to do is leave that in the notes and make it look like as if I was just playing a guessing game and I got it right in the first time. So 7 pi over 6 plus pi over 4 is equal to that. So good. So either way, cosine of 7 pi over 6 plus pi over 4, that's a plus. So we apply the formula mnemonic again, cosine, 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 so I'm missing 2 more. And then sine, sine, and sine. Okay, then I got to simplify this expression. So I need cosine of 7 pi over 6 and sine of 7 pi over 6. Those are the two new ones, because pi over 4 I know very, very well. Pi over 4 is this guy. So we're just looking at this one for pi over 4. For 7 pi over 6, we're talking about this one over here. So 7 pi over 6 is this one. So if I extend the circle, which I'm going to have a hard time doing because my circles are crap. We're talking about this point out over here. I could try my best to extend this part of the circle, which I won't really need it for the rest of the problem, I think. But here's the rest of the y-axis. Now we're talking about that point right here, which that point has the coordinates, so I got to figure it out. If you remember how to do this, it's going to match the 30-degree one, because this right here is 30 degrees this way. It's going to match the 30-degree one almost exactly, except for 2 negative signs. We're in the third quadrant right now. So instead of square root of 3 over 2 and 1/2, it's negative square root of 3 over 2. negative 1/2. And this one is cosine, and this one is sine. And those are half of the answers that I was already looking for anyway. So cosine of negative square root of 3, or cosine of 7 pi over 6. I'm going to zoom back out so I can see them both. Cosine of 7 pi over 6, negative square root of 3 over 2, which with that unit circle, it makes it super easy. I just copy straight what the x and y coordinates are. What you're responsible for knowing how to do is figuring out how to draw that angle and figuring out what those x and y coordinates are based off of the first quadrant. But if you know the first quadrant values, everything else is easy. So cosine of pi over 4, we know that that's square root of 2 over 2, minus sine of 7 pi over 6. Here's the problem. The formula already has a minus. The value for sine at that angle is already negative, so I need to put a double negative on that. 1/2 times sine of pi over 4, which is square root of 2 over 2. We filled in all the values that we need. Now it's just simplification that's left. So if I simplify the first one, negative square root of 6 over 4. The second one, negative, negative, positive, so that makes a positive. So that's plus square root of 2 over 4. And there's my answer for part B. That's completely, well, no, that's not completely simplified. So I'm jumping the gun. This is negative square root of 6 plus square root of 2 over 4. You can go ahead and box that. There's nothing wrong with that. Unless you think there's something wrong with the way it looks, you don't like the way it looks, it's 100% simplified, completely valid mathematically, but maybe you don't like a leading negative term, square root of 2 minus square root of 6 instead over 4. Now for those of you with a completely different OCD where you don't like the bigger one towards the back, you have square root of 2 first, and that's a smaller number, whatever, whichever you prefer. So if you don't want one that's leading negative, you choose the second one, the one on the right. But they're both fine, 100% for either of the two. So that's letter B, and that's based off of the unit circle again. So unit circle, of course, is very, very important. It's going to show up a lot. In the second half of Chapter 7, when we're solving equations, we're going to be using the unit circle again over and over and over. Letter C, cosine of 173 degrees times cosine of 83 degrees plus sine of 173 degrees times sine of 83 degrees. This one we've already seen in class, so the way to get that one done, it's no longer a tricky thing. Hopefully you remember, and you should have notes on this already. But what they're doing here is just an expression, and that's supposed to equal to something, which I'm not going to do those individually and then try to multiply each pair and then add them together to see what we get. No, that's something a lot simpler than that. It has to do with these up here. So the sum or difference formulas for cosine, and it's one of these two. And it's the one that's on the bottom, the difference formula. So this one is the one we're looking at. And what do I say that? If you look at the right-hand side, cosine, cosine, plus sine, sine. This is a cosine, cosine, plus sine, sine on this side. So that means it's equal to a cosine of an angle minus cosine of another angle. Now, which angles? Cosine of the first, and then minus the second. So it's cosine of 173 minus 83. So it's just the right-hand side of the setup for cosine of 173 minus 83 in degrees. So what I do then is I subtract those out. It's cosine of 90. 173 minus 83 is 90. So we want the value of cosine of 90 degrees, and that's just a unit circle value. So I already have the unit circle here to the side. What's cosine of 90? It's the x-coordinate on 90 degrees. That's 0. So my answer is 0. Since we do know what cosine of 90 is, and I do hold you guys responsible for knowing how to find cosine of 90. And that's it for example 1. Those are parts A, B, and C. So we'll move on. Cofunction identities. Now, they placed the cofunction identities in here. One, because we can now prove them, or at least we could prove the cosine one now. Cosine of 90 minus theta, you can use the difference formula with 90 and theta as A and B, and you can prove it now. Now, the reason why they're showing all 6 of them, now we've already seen all 6 of these, and the way to argue for the truth of all of these, there's several. But the major one, we just finished seeing chapter 6 with all the graphing stuff. If you remember correctly, cosine and sine have the same shape. They're just shifted versions of each other, and their shift is exactly 90 degrees. Tangent, cotangent, again, same exact shape. Well, one of them's inverted. So they're almost the exact same shape, just inverted. And by inverted, I mean a reflection about the x-axis. And they're also 90 degrees difference from each other. So that's what this is all about, the 90 minus theta. So there's a reflection in there, and then there's also a shift by 90 degrees in there. And then secant and cosecant are also equivalent except for a reflection and a shift by 90 degrees as well. So that's what these are saying. It's a summarization of how those graphs are related to each other. So cosine of 90 minus theta is sine of theta. Sine of 90 minus theta is cosine of theta. Tangent of 90 minus theta is cotangent of theta, and so on. This one's tangent. This one's cosecant. This one is secant. And those I'm going to prove in the proof video, not in this video. So these won't be shown as a proof in here. So example 2. Actually, I'm going to skip example 2. That's just showing how we can use these here, which I'm not going to go ahead and go over those. I want to concentrate on the sum and difference formulas. So sum and difference. The sum formula for sine, there's a proof for it, and I'm not going to show you the proof, or I'm not going to detail the proof. The proof we've already seen in class, and these are the notes from class of the proof for sine of a plus b. And sine of a plus b is equal to cosine a, or sine a times cosine b, plus cosine a times sine b. And here's the reason why they showed the cofunction identities. You need the cofunction identity as part of the proof for the derivation, or as part of the proof for the formula, to show that it's actually true. So it's part of the actual proof process. So this one, sine a plus b, is sine a cosine b. This one is plus, there's no sign change, cosine a sine b. So what you do is, for the first part, sine a first, cosine b second, and then you switch those two for the second, so cosine a then sine b. So every possible combination, sine a, cosine b, cosine a, sine b. And you don't change the sign. So no sign change for sine. There is a sign change for cosine, but not for sine. Same thing here. This one's sine a, cosine b, no sign change, cosine a, sine b. Tangent sum or difference formula. Now that's not one that I proved. That's one that I left as a proof for you guys to figure out on your own, because I was eventually going to test you on it. It doesn't look like that's going to end up happening though. Since I'm not going to be able to give my dual enrollment students paper-based exams at this point until STC says otherwise. Right now we're all online 100%. So most likely it's just going to be multiple choice tests for the remaining STC exams. For non-dual students, just Memorial Pre-AP students, the district is telling us not to give any tests at all. So for the duration of this this situation where we're practicing physical social distancing, we're doing the distance learning stuff, no tests, only minor assessments, quiz grades basically, so homework and quizzes. So that's not really something I'm going to test you guys on, unless for some reason we come back and that's part of a test, but no, not looking like it. So tangent, the two formulas for tangent, the formulas are, they're fractions, and the way that they have it here is that these are lined up so that way that's a fraction symbol. So it's tangent A, no sign change, plus tangent B, over 1 minus tangent A tangent B. And these are multiplied. So those two are multiplied, the ones on the top are being added. So tangent A plus tangent B, on the bottom it's minus 1 minus tangent A tangent B. For the minus, you switch both signs, so that way the top matches the inside and the bottom switches. Tangent A minus tangent B, 1 plus tangent A tangent B. Those are multiplied. So those are my difference formulas for, or my sum and difference formulas for both sine and for tangent. You add those to the cosine ones, and those are 6 total for just the sum and difference formulas. So what we'll do for the rest of the section is just practice using these formulas. We're not going to derive any of them or prove any of them. Okay. Example 3. Find the exact value of each of these expressions. There's a sine, there's a tangent, and there's another tangent for part C. And let me look ahead real quick. There's an example 4. There's an example 5, and that's the last one I believe that we chose to do in class. There's an example 6, which I'm not going to assess you on whatsoever. There's an example 7, which I did not have time for in either of my classes, I think. We'll see. I might end up doing that one, but it's just another verification problem. But for sure, examples 3, 4, and 5. Those for sure. Those are the ones I want to concentrate on. So we'll look at example 3. Sine of negative 15 degrees. So there's a couple of things we can do. One of them is the way we started off example number 1 was by applying the even-odd identity for cosine. The nice thing about cosine is it's even. That doesn't apply for sine because it's odd. So if it's an odd function, in this case for sine, the negative sign doesn't disappear, it just moves. So you can leave it inside or you can write it outside. So this would be sine of negative sine of positive 15 degrees. And that's not really helpful. So I'm just going to end up leaving it as a negative sign. What would have been nice is if it were an even function and you were just able to delete the negative sign altogether, but we couldn't do that. All we could do is move it. So wherever we move it, it's probably better just to leave inside or to leave the negative inside. And the reason being it's because I can leave the negative as the result of subtraction, subtracting a small number and a large number in a specific order. Small first, then minus the larger. So in this case, 15 degrees is the difference of 30 and 45. Now let's write it in that order. Sine of 30 degrees minus 45 degrees. Not supposed to be a degree symbol up on here. And if I subtract them in that order, you get a negative 15 degrees. So that's why I want to keep it that way. You could just leave it that way. Sine of 30 minus 45, and then we apply the difference formula, which is this, I don't remember, the first or the second, one of the first two. That's the second. So sine A cosine B minus cosine A sine B. So this is sine A is 30, cosine B, cosine 45. You keep the sign minus, cosine of A, 30 degrees, sine 45. And then we have to figure out what each of those things are. At this point, I don't want to look at my unit circle for help. We should have these things memorized. So you want to practice still keeping these in your memory. Sine of 30 is 1/2. Cosine of 45, square root of 2 over 2. That one, if you don't memorize, it's pretty bad. Okay, so minus cosine 30. That's minus square root of 3 over 2. Sine 45, square root of 2 over 2. Again, pretty bad if you don't know that one already by memory. So 1/2 square root of 2 over 2 minus square root of 3 over 2 times square root of 2 over 2. And multiplying these things after a while, you get used to them. This is square root of 2 over 4 minus square root of 6 over 4. And we could just combine the top into one fraction, square root of 2 minus square root of 6, all divided by 4 on the bottom. And that's it for that one. So the sines and cosines are pretty easy if you can get like a 15-degree analog. So something that's related to 15 degrees some way, somehow. Like 75 is a 15-degree analog. You would subtract 15 from 90, you get 75. So they're very related. If you look at letter B, 13 pi over 12. So a 15-degree angle is the same thing as a pi over 12 angle. So really these are the only ones we're going to be able to do these for, because if we subtract 30 degrees, 45 degrees, you get 15 degrees. It's kind of hard to subtract two special angle values to get anything other than the 15-degree angles. So that's what we're going to be seeing over and over, and especially in the homework, you'll be seeing a lot of these types of examples with the over 12 situation or a 15-degree, 75-degree situation. So earlier, we changed 13 pi over 12 to degrees, split it up, and then changed those two back into radians. Let's see if we can try to get it right the first time without having to go the route of changing degrees. 13 pi over 12. So then we start asking ourselves, what are two fractions that when I add them I get 13 over 12? And I don't want them to have 12s in the bottom, though. That's the problem. Because if it has a 12 in the bottom, it's not a special angle value, and I'm not going to be able to resort to using a unit circle. So I want things that look like pi over 12, or pi over 4, pi over 2, pi over 3, pi over 6. 2, 3, 4, and 6 are the ones that we're really looking for. So how do I get that done? Well, before we start thinking about, well, how do the 4s, 6, 2s, 3s come into play, maybe I can leave it as a 12 for now and try to get numbers that reduce down to 4s, 3s, 2s, 6s, and so on. So I have a pi over 12 plus another pi over 12, and hopefully they're going to end up reducing down to like a pi over 6, pi over 3, pi over 4, stuff like that. So all I really care about at this point is the 13. How do I split up a 13 so that way those two numbers reduce with the 12? So let's say, for example, if you wanted to try 1 and 12. 1 and 12 is bad because the 1/12 doesn't reduce. It stays as a 1/12. Let's say 2/12. Let's just go up the list. 2/12. And what would that leave? 11 pi over 12? I don't like that one either because 11 over 12 doesn't reduce. So 1 and 12 suck. 2 and 11 also suck. Let's say 3 and 10. That was not so bad. Because 3 over 12 reduces to what? That's pi over 4. 10 pi over 12 reduces to, maybe I could have chosen better numbers because that's going to end up being a 5. I could deal with the 5. What's that going to be? 5 over 6? Yeah, I could deal with that. 5 over 6 is a special angle value. So we'll try to figure out what the 5 over 6 is at in just a little bit. But pi over 4 is nice. And then 5 pi over 6. It's also nice. That's in the second quadrant, I believe. So what we're going to do, though, there's still a little bit of there's still a little bit of having to hide our sources. So I'm only trying to save space, and I might not need to save the space anyway. But tangent of, and I'm going to steal all of this and put that here. I'm going to pretend as if I had done that in my head. So tangent pi over 4 plus 5 pi over 6. And what I'm going to do at this point, once we've successfully split them up into two fractional values that add up to 13 pi over 12, I'm going to go back to this as a reference. And where are they at? They are up over here. I am looking at the plus one. Yeah, so the one on top. Tangent A plus tangent B divided by 1 minus tangent A times tangent B. So I'm see if we remember that. Tangent A plus tangent B. So tangent pi over 4 plus tangent 5 pi over 6, all divided by 1 minus those two multiplied, tangent pi over 4, tangent 5 pi over 6. So we got to figure out what either of these two values are, and then we just plug them in and see if we can simplify. So the reason why I wanted the space is because if you look at the form, there's a plus on top, there's a minus on the bottom. They're going to be fractions. Fractions within a bigger fraction. I need some space to figure out what that's going to be. So most immediate problem first, what's tangent pi over 4? If you remember correctly, that's just 1. Tangent is sine over cosine. Sine and cosine at pi over 4 are square root of 2 over 2. When you divide those two numbers into each other, you get 1. That's the easy one. What's tangent 5 pi over 6? It's going to be a negative something. How do I know it's negative? Tangent in the second quadrant is negative because sine's positive, cosine's negative. So what I'm going to do is I'm going to go back to my crutch, the unit circle. I want 5 pi over 6. 5 pi over 6 is 30 degrees before 180. So this is 5 pi over 6 this way. And it's starting to get a little messy, but whatever. So 5 pi over 6, it's the same thing as a 30-degree reference angle this way. Or pi over 6 radians. So the reason why I say that, it's because I want to reference the 30-degree angle point. And it's the same x and y coordinates, just one of them's negative. Negative square root of 3 over 2, positive 1/2. The y is positive, the x changes to negative. So it's just geometry reflecting and looking at the mirror image across the y or mirror image across the x and finding out what the signs are. But the x coordinate, y coordinate values are exactly the same. Square root of 3 over 2, 1/2. So this one's cosine. and this one's sine. So then I got to do a little bit of work. Tangent, and I'm doing that over here down here, tangent of 5 pi over 6 is equal to sine 5 pi over 6 over cosine 5 pi over 6. If we didn't already know how to figure that out, or if we didn't already have that memorized, which those are harder to memorize than the sines and cosines, because you got to do division. So here you divide them. Sine of 5 pi over 6 is 1/2. And then we're dividing that by cosine of 5 pi over 6, which is negative square root of 3 over 2. And we're dividing two fractions, so that's ugly. So you just take the top fraction, multiply by the reciprocal of the bottom fraction. So 1/2 times negative 2 over the square root of 3. The 2's will cancel, the negative stays, and you get negative 1 over square root of 3. And that is the same thing as negative square root of 3 over 3 when you rationalize. So that is the tangent of 5 pi over 6, which I'm stealing. And I'm writing that over here. Negative square root of 3 over 3. That's going to go down here as well. So 1 minus, you multiply 1 and negative square root of 3 over 3. When I simplify, the bottom expression that is, well, the one on the top is going to be 1 minus square root of 3 over 3. The one on the bottom is going to be 1 plus now square root of 3 over 3. It would have been nice if that had stayed negative on the bottom, because then those would have canceled out to 1. But now they're different by a sign in between. So then I got to figure that out. So what we're working with, I'm going to write that over here because I need the space. And I want to start it back over here. Square root of 3 over 3. 1 plus square root of 3 over 3. Now one thing we can do right away to make this look nicer, multiply both top and bottom by 3. And what's the goal there? If I distribute the 3 into both, and then both again on the bottom, you get 3 minus square root of 3. No more fraction inside. On the bottom, 3 plus square root of 3. The 3's cancel on the fractional one. So that's what we have so far. And as nice as that looks, that's not completely simplified. If you were taking a math exam with STC or with me even, any other math teacher, self-respecting math teacher, would not take that as completely simplified. And the reason being, square root on the bottom. So I'm going to get rid of that square root that's on the bottom. And the only way that I can get rid of that square root on the bottom is to effectually square that square root of 3. Now, one nice way to square out that square of square root of 3 is to multiply by its conjugate and turn that into a difference of squares situation. So we're concentrating on the bottom, and I want to make a difference of squares in the bottom. But in order for me to legally multiply a difference of squares into the bottom, you must also multiply it into the top, the exact same thing. So that way they effectually, or it's the same thing as multiplying by 1. Problem is I have to deal with that perfect square on the top. So the one on the top, which I'm not going to cover too much the algebra stuff, that's a perfect square. There's a shortcut. You square the first, so 3 times 3, 9. You multiply the first and the second, so that's 3 times square root of 3, but you double it. That's minus 6 square root of 3. And then you square the second, plus 3. So where's that coming from? That's coming from the idea that in this case, this is minus a minus b squared, which is the same thing as a minus b, which is what we're dealing with, is a squared, so you distribute, minus ab plus b squared, which is a squared minus 2ab plus b squared. You should be able to see how I got the result up here on the top from this. Notice there's 3 terms. It matches those of the 3 terms. You should be able to figure it out. So on the bottom, that's a difference of squares. 9 minus 3. A minus b times a plus b, which is what we're dealing with on the bottom, is a squared minus b squared. You just square each term, subtract them. And what we get is, well, 9 minus 6 squared root of 3 plus 3, I could do the 9 and 3. That's a 12. Minus 6 squared root of 3, all divided by 9 minus 3 is 6. You would divide both of those terms by 6. You get 2 minus the square root of 3. And there's part B. Okay, so like I said, there was going to be a bunch of stuff that we had to do. The majority of this was algebraic simplification of the fraction within a fraction. So we were done with the trigonometry at this step. Everything else that followed that step was algebra. So a lot of the times that's going to be what you're going to deal with in calculus if you take calculus next year. Those of you that are planning on taking a calculus class next year, whether it's at Memorial or if it's at whatever university you're going to be going at, if you're a senior already, 99% of the time, what causes a student to quit calculus and drop it altogether is not the calculus. It's the algebra that they forgot along the way. So the application of the calculus stuff is pretty simple. It's a lot easier to remember than a lot of this trigonometric stuff, by the way. But the stuff that hurts is the algebraic simplification at the end. If you don't know your algebra, now you're going to have a tough time with calculus. That, in my opinion, is the toughest part about calculus. Remembering all the algebra from before that your teachers beforehand didn't teach you, or that you didn't learn. Alright, so in this case, we'll go ahead and consider that part done. We'll move on to part C. Part C is another one, just like in the previous example, example 1, part C, where they wrote out the right-hand side of the sum or difference formula, and they had you figure out what the formula had on the left-hand side. Same idea here. So if you look at that fractional expression, it's the same as these fractional expressions for tangent. And we're going to basically just boil it down to the left-hand side, a tangent A plus B or a tangent A minus B. First, you got to figure out plus or minus, and then you got to figure out what's A, what's B. So if you remember for tangent, if it's minus on top, it's minus in the inside. That's tangent A minus B inside. So minus on top means it's minus inside. So I just got to figure out what A and B are. A is 100, B is 70, it looks like. So it's tangent 100 minus 70, which we can continue going. Tangent 30. And I can continue going even further. Tangent 30, well, I don't remember tangent 30 from the top of my head. Some of you might already know that by memory. It's either a square root of 3 or a square root of 3 over 3. And the way to figure that out, sine of 30 divided by cosine of 30 will have the same effect as just taking tangent of 30. Sine of 30, 1/2. Cosine of 30, square root of 3 over 2. So long story short, when you divide those two fractions, the 2's cancel. You're left with 1 over square root of 3. Square root of 3 over 3 is the answer for this one. And that's it for example 3, which we'll look at examples 4 and 5 at this point. This is all we really need for the essence of 7.3, what the formulas are and how to use them. But there are some slightly tougher examples that I don't want to leave you without knowing. So we'll look at examples 4 and 5. And again, we saw these in class, so not a really big deal. But I want you to have these videos available just to refresh, stuff like that. So example 4, write each function as an expression involving functions of theta alone. Cosine theta minus 270 degrees for part A, then you have tangent of theta plus 3 pi, and then sine of 120 degrees plus theta. So we'll look at letter A, cosine of theta minus 270, which we can go ahead and go straight to the formula. Cosine, 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 sine, sine, sine. How do I know that? It's an angle and another angle being subtracted. So it's a difference formula. So just because the theta is variable doesn't mean you cannot apply the formula. We can definitely apply the formula and just leave the variable in there. So that's going to act as the letter A. 270 is going to act as the letter B. Now we could just play as if that were the case. So cosine of A, which is theta, times cosine of 270, which is B. Cosine, 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 then sine, sine, sine. And there it is. So then I got to simplify. Cosine of theta, sine of theta are not going to be able to simplify. Those are going to stay the way they are. Cosine of 70 degrees, I have to figure that one out. Or 270 degrees. Cosine of 270. 270, if you remember correctly, is the negative y-axis. So if I were to draw that somewhere, So draw a unit circle. 270 is this angle. So that's on the negative y-axis. And cosine is the x-coordinate at that particular angle, which would be 0. So that's just cosine of theta times 0, and that's 0. Plus sine of theta. Sine of theta is variable. That depends on the value of theta. Sine of 270, though. Sine of 270 is the y-coordinate for that same point at 270 degrees, and that has a y-coordinate of -1. So times -1. The 0, I don't need to write the 0. -1 times sine is negative sine. And that's the answer for letter A. Sounds pretty simple. We're going to do the same thing for tangent. So I'm probably going to write that down here. Tangent of theta plus 3 pi. That's a sum formula. So the sum formula has a sum on top. Tangent theta plus tangent 3 pi. That's divided by 1. You change the sign on the bottom, 1 minus. Then you multiply both. Tangent theta, tangent 3 pi. The only one here that I got to figure out is tangent 3 pi, which I'm going to do that on the side. Tangent 3 pi. And the normal way that we do this is sine of 3 pi divided by cosine of 3 pi. Sine of 3 pi. What's 3 pi? 3 pi is this angle. This is 2 pi, and then you go an extra pi. That's here. So we're talking about this point, and that's the same thing as pi. 3 pi and pi are essentially the same angle with regards to a trigonometric function. So if I wanted to calculate sine or cosine of 3 pi, it's the same as if I'm calculating the sine or the cosine of just pi. So cosine is -1 at that point. Sine is 0 at that point. So let's remember that. Sine is 0. Cosine is -1. I don't care about the -1 on the bottom. The top is 0. The whole thing's 0. So tangent 3 pi is 0. So that's this one. And this whole thing is 0 because that one's 0. So we're left with tangent theta on the top. 1 minus 0 on the bottom, which is 1 on the bottom. Tangent over 1. Tangent theta. So if I take tangent theta plus 3 pi, you just get tangent. So letter C. Sine of 120. There's a formula for a sum. Sine of 120 cosine theta. You don't change the sign for the sine one. Cosine 120 sine of theta. And then you simplify. Sine of 120, cosine of 120. That's where I go back to my unit circle, which I might want to go back to this one because this one's nicer. 120, crap. So this is already too messy. But 120, I'll do that in a different color. Let's say green. 120 is up here. So 120 degrees. And 120 degrees shares the same reference angle as 60. So that means the coordinates are the same except for the x. -1/2, positive square root of 3 over 2. So I'm stealing the x coordinates from the 60-degree angle, and I'm just negating the x coordinate because now we're in the second quadrant. So then -1/2 square root of 3 over 2. This one's cosine, this one's sine. Let me remember that. So for cosine, -1/2, sine, positive square root of 3 over 2. So sine, positive square root of 3 over 2. This changes to cosine, or that stays the same to cosine theta, plus this was -1/2 and sine theta stays as is because theta is a variable. So sine theta. Then we simplify, which I don't think I can. Square root of 3 over 2 cosine theta. The only thing I can do is change it to a -1/2 sine theta. If there's anything else I might be able to do, is maybe factor out the 1/2 if I want to, but there's no need for that. Either of these two are fine. And that's it for example 4, unless there's a part D, but I don't think there was a part D. So in this case, we're just applying the sum and difference formulas just like we did earlier, but they left one of the two angles as a variable. And what that means is the end result should still be a function of the variable that was left over. Try to simplify as far as you can go. And there's that for example 4. The last example is kind of a tough one. There's a few of these examples on the homework for 7.3, and then for the review for 7.3, 7.4 if you're a dual student. Pre-AP is getting a new assignment, 7.3 to 7.4, as a homework. Dual Enrollment's getting a new assignment. They already have a 7.3, 7.4 assignment. They're going to get a review for 7.1 through 7.4. So for that, there'll be some problems like this for example 5, and these are kind of tough, so this one you want to make sure you learn very, very well. So for example 5, they're going to give us some information, but not all information. They want us to find out these things. There's a part A, B, and C, I think. Yeah. So it's just A through C. And then once we're done with A, B, and C, we're done with the entire problem and the section. So then example 5 starts with, suppose angles A and B are written in standard position such that cosine A is, that's important, cosine A is -7/25. And then they're also saying pi is less than A is less than 3 pi over 2. We said this in class earlier. This is just a fancy way to say that A is found inside quadrant 3, because it's between pi and 3 pi over 2. Pi is 180, 3 pi over 2 is 270. That's quadrant 3. Sine B is equal to -3/5. And then B is found in quadrant 4, it looks like. Let's keep it consistent. Roman numeral, Roman numeral. Okay, so quadrant 4. And with those two bits of information, find sine of A minus B, and then so on, tangent of A minus B, and then the quadrant of A minus B. So then I got to figure that out. So for now, let's ignore what they gave us. And I know how to do this. Sine of A minus B, that's just a formula. Sine of A, cosine B, keep the sine, cosine B, sine A. And now I go back to the stuff they did give me. And if I look at the stuff that they gave me, then I can fill out some of this information. I don't have sine A, that's unknown. I don't have cosine B. Oh wait, I think I did this wrong, by the way. This one's wrong. This one is cosine A, sine B. Very sorry about that. So if you were annoyed by that the whole time, I'm very, very sorry about that. But either way, so cosine A, sine B in the second portion. I don't have sine A, cosine B, so the first part of it is unknown right now. I know the second half, though. Cosine A was given. That's -7/25. And then sine of B is -3/5. So all that information, let's see, I got to figure out the rest of it. There's 4 things: sine A, cosine A, sine B, cosine B. I only know half. So this is probably where you'd get stuck. How do I find the other pieces of information, sine A, cosine B? So this is where I go back to what we learned in the first section. You might want to go back to section 7.1. So I only did one example in section 7.1 because it was a very short section. There were 2 other problems, but those are the 2 I'm not testing over. Not really, really important. But go back to 7.1 to see how I reason from here on out. So they gave me cosine A. I don't have sine A. And I want to find out what sine A is. You use a Pythagorean identity. So to find sine A, you do sine A is equal to plus or minus the square root of 1 minus cosine squared A. And again, if you don't remember how to get that, go back to 7.1. So there's a video on how to figure that one out. So I'm not going to go over that one slowly, how to figure that out. But basically, sine squared plus cosine squared for any angles equal to 1, you can solve for either one of those 2, and that's the expression that I have here. And I solve for sine, because that's the one that we want. So I know cosine A, we square it, plug it into the formula. -7/25 gets squared. So I didn't need the negative inside of it because it's going to get squared anyway. So 1 is going to be plus 49 over crap. What's 25 squared? 625. I know some of my squares, not all of my squares. 15 or 25 is an easy one. 625. That one's an easy one to memorize. 15 is another easy one. That's 225. 49 is an easy one. 7 times 7. Okay, so what we have to do is we have to simplify the expression inside the square root. 1 plus that. We're combining two fractional expressions. You think of the 1 as a 625 over 625. So 625 plus 49 over 625. What is 625 plus 49? That's 6. Oh no, is that plus or is it minus? That's minus. I think what I was doing is I was combining these two negatives into a positive, but you don't do that because that negative gets squared and it goes away. So the minus remains. So it's 1 minus 49 over 625. Same thing as 625 minus 49, all divided by 625. So now I got to subtract those. It's 5 for sure. Is that 76 over 625? And just to make sure, you add 49 to 576 to see if we get the same thing. It's the same thing as adding 50 minus 1. And yeah, that's correct. Okay. Now 576, I believe, is 14 squared. So this is plus minus 14. Oh no, not 14. 24. I got my numbers wrong. It's 24 squared over 25 squared. Square roots get rid of that. So plus minus 24 over 25. And the reason why I remember, there's a special right triangle. If it's a right triangle, it's 7, 24, 25. That's what we call a Pythagorean triple. Pythagorean triples are whole numbers that are also sides of right triangles. So the point is whole numbers. There's another easy one. The 3, 4, 5 is a right triangle, and so on. There's a bunch more. So if you don't know your squares, but you know those right triangles, these are easy problems too. So anyway, that is sine of A. Now here's the thing. I need to choose a sign. Is it positive or is it negative? We're doing this for the angle A. And A, we remember, is in quadrant 3. Therefore, sine is negative. So we get rid of the positive. This is sine A. I'm going to kind of box that, not really box it completely, because that's not the answer of the problem. That's just part of it. So that's negative 24 over 25. I still need to find cosine of B, and that's going to suck. It's going to require about the same amount of work as sine of A. So we'll go ahead and do it. Cosine B is plus or minus square root 1 minus sine squared B. Same way that sine squared, or sine A, is equal to plus or minus square root 1 minus cosine squared A. So that's coming from the same Pythagorean identity. So we just plug in what we have. 1 minus sine of B is negative 3/5. We square that. Then we subtract it from the 1, square root that, figure out the sign, and that's cosine. So that's going to be plus minus square root 1 minus, I like these numbers better, 9 over 25. That would be 16 over 25 if I subtracted the from the 1, which becomes 4 out of 5. And that's the 3, 4, 5 triangle, by the way. So cosine is either plus minus 4/5. So we are in quadrant, what is it? For B, quadrant 4. Therefore, cosine is positive. So it's only the positive. This is cosine B. I'm like half boxing that because that's information that's useful. This is positive 4/5. And here's the thing. I want to see if I could try to simplify that expression. There's a minus and two negatives. three negatives essentially become one negative. So I could just write minus 7/25 times 3/5. You can group any two. There's going to be one left over, one negative sign left over. And then that's what we have so far numerically. Now I just got to simplify that. So we end up getting, I got to multiply 24 and 4. 24 times 4, I can simplify that to 12 times 8. 12 times 8 is 96, so that's negative 96 over 25 times 5 is a cube number you should know, 125. 7 and 3 is 21 over 125. Now I got to multiply, or I have to add 96 and 21. So you get a 7 in the end. It's going to be a negative 7 at the end. You don't carry over anything, that's 11. So 117 over 125, negative. Now 125 only has a factor of 5, which does not divide the 117. Therefore, these are relatively prime. You can't reduce them. So that's part A. And look at all that work just for letter A. Now the nice thing is, since I already saved the values of sine of A and cosine of B, I already have that work done. I don't have to do that work again. We should be able to figure out letter B fairly easily. So hopefully. So there's a couple of things we could do. Tangent of A minus B. There's a formula for tangent A minus B. And I could do that. Or I could also maybe say that tangent of A minus B. So I could probably try doing this. So here's the first. Tangent A minus tangent B over 1 plus tangent A tangent B. That's the formula I'm talking about. That's the first way you could try. The other way you could try, different route. We already have sine of A minus B. Try to find out what sine of cosine A minus B is, and then just divide the two. Two different routes you can take. Now I don't want to take the time to show both, and since we're practicing using these new formulas, we'll go the first route, which applies the formula for tangent. What's the problem with that? Problem with that is I don't know tangent of A or tangent of B, but we can basically use the same idea behind this thing and just divide sine and cosine for A and B. So yeah, I'll forget about that. And on the side, tangent A. And then also tangent B. Tangent A is sine A over cosine A. I have both of those quantities, cosine A and sine A. So sine A we found negative 24 over 25. That one I had to do using the Pythagorean identity. That's divided by cosine A, which was given, negative 7 over 25. So when all is said and done, these you can do tons of times, practice them over and over and over. They have the same denominators. Those denominators cancel out. You're left with negative 24 over negative 7, which is basically 24 over 7. Those don't reduce. Tangent A, because 24 does not divide, or 7 does not divide 24. So really quick, this thing right here, those I know how to do really quickly. Let's say this is A over B divided by C over B. They have the same denominator. Before I was a teacher, I spent a lot of time tutoring, private tutoring college students when I was in college. So I would put up flyers to advertise my tutoring services, and I would tutor students in pre-calculus, calculus, college algebra, stuff like that. I also spent a lot of time with other tutors because I had a job on campus when I was in college as a part-time tutor in a tutoring center. So I was working alongside other tutors, and there was this one tutor that had a funny name for this rule. They called it the law of the, well, no, it was, he was from Mexico, so he would speak primarily in Spanish. So it was the law of the torta, or the law of the sandwich. But either way, so they called it the sandwich because you have two fractions, and there's like a, I don't know where that comes from. But anyway, the idea is that these two denominators cancel out, and the shortcut is just A over C. That's the law of the sandwich. So the way to prove it, though, A over B divided by C over B, which we can do this painfully slow, which I don't like doing this over and over and over. I just go to the shortcut. Shortcut's easy. It's A over B. You multiply by the reciprocal of the bottom, B over C. And these two multiply to A times B. Those two multiply to B times c. The b's cancel. You're left with a over c, same as this. So it's a shortcut I know, and I use a lot. So I definitely used it here. So they had the same denominator, 25 and 25. Kill the denominators, just write the numerators over each other in that same order. And then the negatives cancel out. See if the same thing happens with tangent b. Tangent b is sine b over cosine b in that order. Sine b, I don't remember if that one was the one that was given. Yeah, it is. Negative 3/5. So negative 3 over 5 divided by cosine of b. We worked for that one, and that one's here. Oh, it's right there. I was moving around, and it was right up on top. 4/5. Again, the 5's cancel. You're left with negative 3/4 for tangent. And there's the work for tangent b. And those are just smaller little parts of a bigger problem. And what's the bigger problem? This one. Tangent a, 24 over 7, minus tangent b, negative 3/4. So that's going to end up being plus 3/4 because a minus minus, divided by 1 plus 24 over 7 times negative 3/4. 24 over 7 plus 3/4 over 1 minus 24 times 3, let's see, and then we have a 7 and a 4. The 4 divides the 24, that turns it into a 6. 6 times 3. 6 times 3 is 18, and then over the 7. So here, this is what I was doing verbally. 24 times 3 over 7 times 4. The 24 and the 4 divide to 6. 6 times 3 over 7. 18 over 7. And that's just a little extra work that I did over here. So then, there's a problem with this one, especially the one on the top. The 7 and the 4 don't match. But I kind of want to ignore that for now, because I have a 7 on top and a 7 on the bottom. So I might want to do this in pieces instead of just in one shot. So I'm going to multiply everything by 7, and that's going to kill at least the 7 denominators. It doesn't address the 4 yet, but we'll do that in the second step. So if I multiply everything by 7, you get 24 plus 21 over 4 over 7 minus 18. So only the one with the 4 on the bottom stayed as a fraction, and it turned into 21 over 4. Because you're multiplying 7 to 3/4. 7 and 4 don't reduce, so the 7 just multiplies with the 3 then. 3 times 7 is 21, hence the 21 over 4. Now I'm going to multiply everything by 4 to kill that remaining denominator. So 24 times 4, we had said that earlier, right? 24 times 4 was 96. Plus, that's just 21. 4 times 7, 28. Minus 18 times 4. 18 times 2 is 36. Times 2 again is 72. Whoops. So I got to figure that out. 96 plus 21 is 117. 28 minus 72, that's a negative. So negative 4 at the end. And that is, let's see, 44, I believe. So if you take 44 plus 28, yeah, you get 72. So here's the answer for tangent of a minus b. And that's what we have so far. So far that's a lot of work, and we've spent the most time on just this one problem, and we're not even done. Which, part C, well, we're essentially done, because part C is just asking for the quadrant of this angle a minus b. So where is this angle found in what quadrant? So for that I have to look at parts A and B collectively. For part A, sine is negative. For part B, tangent of the same angle is negative. So we're talking about an angle for which sine and tangent are both negative. Sine is negative in both the third and the fourth quadrants. But of those two, tangent is only negative in the fourth. So we're saying that this angle is in quadrant 4. That's because sine of a minus b is negative, and tangent of a minus b is also negative. So the first one right away told me that it's either quadrant 3 or 4. The second one, well, tangent's negative in either quadrant 2 or 4. The overlap is 4. So they both have 4 in common. So that's where we're getting that from. And there's the end of that beast of a problem. And that's it for 7.3. There will be a homework assignment to follow 7.3. So this video will cover just the notes for just 7.3. The homework assignment will also have stuff for 7.4 in it as well. So there's that for now.